But thank you all for coming. So yeah, as Hog said, this talk is part of my 5-year review, and so I'm going to tell you about what I've been doing at CCA over the last 5 years and what I hope to do in the future. And at first I was like, great, this gives me a lot to talk about. And then I was like, oh my God, this gives me a lot to talk about. So I hope you're ready for a 3-hour colloquium. I'll try to restrain myself and cut down the picture a little bit. But to start with the biggest picture, start with a little context, the good old existential questions. Who am I? So my background is very much as an observational astronomer. I've spent well over 100 nights sitting at a telescope, and that background really informs what I do today, which is less sitting at a telescope and more developing data analysis methods based on that understanding of how the data work from photons on. I'm really motivated by the challenges of trying to push our data analysis to achieve the highest possible precision signals in the data. And the scientific context in which I'm doing this is stars and exoplanets. I would say the big science question that motivates me a lot is trying to achieve a picture of our solar system in context with other star planet systems, like and unlike our own. I'd like to be able to answer quantitative questions about things like how common is the Earth? We know all of these detailed things about the sun, what it's made of, how it behaves over time. How common are those sorts of behaviors that we see in detail here? How biased of a picture of the galaxy and the universe are we getting? So this is an exciting time to be working on this. I would say the main hurdle at the moment is finding other Earth-like planets. To really say something is a solar system analog, you'd like there to be an Earth analog in it. And at the moment, we have yet to find a true Earth analog around a solar analog star. So I'm working towards trying to find Earth-like planets, and that's what I'm mostly going to be focusing in on today for this talk. And for the sake of honesty, I'd also like to find aliens, but I'm not going to talk about that today. So how do we find Earth-like planets? And specifically, the Earth-like planets that I'm most interested in are the ones where we stand to learn more information about them. They're close by, amenable to follow-up, maybe someday sending a probe there to look for those aliens. I'd like it if we could do this within the next few decades, if possible. So what of the many different flavors of exoplanet detection can get us there? The method that you've maybe heard the most about, it's found the most exoplanets, is transit photometry. That's where you see the planet pass in between the star and your line of sight, and you see a dimming of the star. Transits are a great tool for detecting planets en masse, but they're not great for Earth-like planets because you have to get so lucky in the geometry of being lined up in that narrow range of angles where you actually see a transit. The transit probability falls off geometrically as the planet gets farther from the star, and that sort of cone of transit angles narrows. And as you get out to an Earth analog, you're down to 0.5% probability of it actually transiting. So we're probably not going to find the closest Earth analogs to us with transits. So I'll cross that off the list. Astrometry has been getting some hype recently. It just found a black hole. It should be able to find an Earth, right? Well, an Earth is a lot less massive than a black hole, unfortunately. And there are no currently planned astrometric missions that are going to get down to the amplitudes of Earth mass planets. So while astrometry will be great and transformative for exoplanets, it doesn't work for this use case. Microlensing is also getting some hype with the Nancy Grace Roman Space Telescope, which should find lots and lots of microlensed planets. Microlensing can probably find some Earths, but like transits, they're probabilistically not going to be close to us. They'll be around faint stars. And most importantly, with microlensing, you see that planet once and you never really get to see it again. So they're not good for follow-up and understanding the whole system. So I'll cross that off. Direct imaging is something that we as a community are putting a lot of resources into and hoping for in the future. I think eventually we'll definitely want to take direct images of Earth-like planets with things like the Habitable Worlds Observatory that NASA is starting to plan for. However, actually finding a planet through a blind search with something like Habitable Worlds Observatory is super expensive. I just learned today that apparently an Earth analog seen with habitable worlds will get about 1 photon per week of integration time. So you're going to be waiting a long time to get those images, and it would be great if it was a follow-up step and we already knew where to look. So it's also beyond my 10 to 20 year arbitrary timeline.
It's not that arbitrary.
Yeah. We're trying to move beyond the existential questions right now. So this leaves us with radial velocities, and I will assert that it is possible to find Earth-like planets with radial velocities. Just so we're all on the same page, when I talk about radial velocities, I'm talking about looking at the spectrum of a star over time, seeing the stellar absorption lines move back and forth to represent the Doppler shift of the star, and then being able to translate that speed of the star as it moves in and out of the plane of the sky into its motion due to the orbit around the common center of mass of the star-planet system. This is a tried and true method that was used to discover the very first exoplanet back in 1995, and it's still going strong today. So how exactly do you use radial velocities to find an Earth? I want to break this down in terms of sort of the experimental design of a radial velocity planet search. So you choose your star that you're going to look at, you point your telescope at it, you send the light through a spectrograph, which looks like that, and basically, and you record a spectrum onto your detector, which looks like this, literally, except with a false rainbow on top. Your spectrograph delivers to you that image and some calibration data that allow you to extract a flux versus wavelength 1D stellar spectrum. You transform that spectrum into a measurement of the radial velocity. That puts 1 point on that RV versus time plot. You keep doing this a bunch of times until you're able to get enough radial velocities over time that ideally you will have found a Keplerian or 2 or 3 or more, and you will have found that planet. So this whole process has been done successfully many times. It takes a lot of steps and like bits of technology along the way, and I'm going to be talking about a lot of those different steps today. But what does it take to do this for an Earth-like planet? Well, the radial velocity amplitude of an Earth is 9 centimeters per second. So in terms of how much the spectrum is physically moving on the detector when the star moves by 9 centimeters per second, it's moving by 12 silicon atoms. So that's not even like in terms of a pixel on the detector. That's like 1/10,000th of a pixel on the detector is the motion. Fortunately, we have a lot of spectrum on the detector, so we can get down to this level if we're really careful. But in order to trust that that shift of 12 silicon atoms is truly from the star's motion and not from the optics of the instrument changing, you need to have your instrument stabilized and or calibrated down to an extreme level of temperature and pressure stability. So there's a ton of engineering work that goes into building these spectrographs. Not only do you have to do all of that, you have to keep that going at that level of stability for a duration of multiple years so that you can see multiple orbits of your Earth analog planet and be confident. And if you have successfully managed to do all of that, we in the business would say that you are doing extreme precision radial velocity. And I think you've earned that title of extreme. This is really hard to do. But there's a lot of people trying to do this. So this is a little sampling of a few of the instruments and teams that are working on this problem, ranging from the NASA and NSF supported NEWID telescope at Kitt Peak to the ESO Espresso telescope and the privately funded and collaboration funded HARPS 3 and EXPRESS. there's a lot of investment of time and resources worldwide that's going into this project right now. But there's also a lot of work that needs to be done here. So CCA and Flatiron Institute are involved in one of these projects, the HARPS-3 spectrograph. Specifically, we're consortium members for the Terra hunting experiment. This is led out of Cambridge. PI is Didier Collot, and Flatiron Institute and Princeton are the only two US-based members. The rest is a large consortium in Europe and the UK. Terra hunting experiment is a dedicated survey trying to find Earth-like planets, and it's currently scheduled for first light in 2025, so coming up. We're using the HARPS-3 spectrograph. These are pretty standard specs for an extreme precision radial velocity spectrograph, super high spectral resolution and long wavelength coverage across the optical, highly stabilized, lots of engineering goes into this. It's actually a close copy of some previous spectrographs with a few tweaks made to improve performance even more. The really unique thing about the Terra hunting experiment is the amount of access that it has in terms of telescope nights. So HARPS-3 is going onto the 2.5 meter Isaac Newton telescope at La Palma, and we're refurbishing the telescope to enable fully robotic operations. And in return for delivering the telescope or delivering the spectrograph for facility use and roboticizing it, the consortium gets guaranteed 50% time every single night for 10 years duration. And that gives a really unprecedented degree of access and flexibility in terms of being able to take lots and lots of data at whatever cadence we want for a long duration of time, and actually makes finding these signals possible. CCA was instrumental in setting the priorities of the Terra hunting experiment. So we're aiming to find exoplanet signals that are close to the sort of Earth analog regime down to 10 centimeters per second. Our top priority from the start has been to find some of these planets. But I think it's fair to say that CCA played a strong role in making sure that we also have as top priorities performing the survey in a statistically robust and reproducible manner such that we can do occurrence rate calculations through this, and to make sure that we're delivering our data, methods, and scientific results to the astronomical community. So these will ensure that we have a legacy value in the data set, that it can be used for things beyond the initial goals, and that we'll have a broad reach for this mission. So through the Terra hunting experiment and other surveys, this kind of work is underway. Now the $1 million question is, will it succeed? Will we find Earth-like planets? That depends on a lot of things lining up and going our way. It's a complex picture, so I tried to kind of throw up a bunch of the different considerations that we have to think about along the way, ranging from the high-level design of the survey, selecting the right targets, setting the right survey strategies, scheduling the observations, and executing the survey in keeping with your goals, to things like making sure that your instrument is working the way it should be and calibrated properly, to data analysis problems at the end, like extracting radial velocities, modeling the signals that you see, and assessing the significance and confidence and validity of your detections. A lot of these things, especially the things at the start, we really have to get these decisions right. If we start the survey and haven't thought through all of this stuff, then the long-term value of the data is really going to be injured. So even though the data from this survey don't exist yet, it's very much a data analysis problem to try and figure out how to make this survey work the best that it possibly can. So I'm going to go through a few of these different things along this whole path now, because I've been working at a lot of different points here. And I'm going to start actually kind of in the middle of the flow from photons to exoplanets with a nice, easy question. So you've recorded your spectrum. how do you turn that into a measurement of the Doppler shift at the time that the spectrum was taken?
Is that what this data actually looked like on the 2D device?
This is a solar spectrum, yeah, taken at extremely high resolution.
But it is the terra hunting data will look like that more or less.
Yes, they will.
You have the laser picture.
Yeah.
Oh, we also have the laser frequency on as well. Yeah.
So the form of data that we see most often is this extracted spectrum, and I'm just showing you a little chunk here around the H alpha line, looking at this stellar signal at very high signal to noise. And the problem of how to measure radial velocity is kind of a fun one to step through because it seems simple on the surface, but there are some real subtleties to this. So how do you measure radial velocity? I think the classic astro answer is that you say, oh, I know that this is the H alpha line, and I know that that's at 65, 63 angstroms. So I will solve my Doppler shift equation to get the velocity of the star. That works great at a certain accuracy, but just using one line is not making great use of all of your spectrum. So instead, you can cross-correlate by adding lots of different lines to your template and simultaneously trying to match all of them to the spectrum. This is kind of the standard way of doing it in the field, but it's limited by the fact that no cross-correlation template is going to perfectly match the unique absorption line pattern of the star that you're looking at. And in fact, you could say, I'm sitting on a ton of information about this star itself. Like my data set is actually probably the best in the world for telling me what the stellar spectrum looks like. Why don't I use that? So you could use a template observation of the star itself, choosing, so these three different colors are the spectrum observed at different times and therefore different Doppler shifts. I can choose one of those and say that's my template. I'm going to throw away accuracy, but I don't really care about that. What I want is precision over time, and I'll be able to tell how much the star is moving. Or I can even take it a step further and do an iterative shift and stack kind of approach where I build an even higher signal to noise template out of all of the spectra. So this seems like the right answer, but if you look really closely, you'll notice that actually not all of the lines are shifting with the stellar radial velocity. That's because these lines that I've circled are telluric features imparted by the Earth's atmosphere. So if you naively try to fit all of the model by, say, cross-correlating against one stellar spectrum, you're also going to be cross-correlating against telluric lines, which have a different radial velocity. What you really need to do is be able to forward model your data as both the star and the telluric features. And this is a little bit hard because we neither have a perfect model of the star nor the telluric spectrum at the level of precision that we need. So actually one of the first things that I did at CCA was to come up with this data-driven model to attack this problem. We called this the Wobble method. It's spelled wobble, but it's pronounced fancier. And it basically just says your spectrum y sub n at any time n can be described as a sum. This is in log flux, by the way, so the sum is a multiplication. But anyway, your spectrum is a sum of the stellar contribution that's determined by the constant underlying stellar spectrum shifted and interpolated to the velocity at time n, plus the telluric contribution. That's an air mass scaled mean telluric spectrum. There's also a slightly fancier version of this model that includes some telluric time variability as well. But basically, the free parameters that you need to learn from this model are all of the radial velocities for your different spectra, the underlying stellar template or stellar spectrum, and the underlying telluric spectrum. And that gives you about 10,000 free parameters in the way that we've set this up. So it's conceptually simple, but hard to actually do the optimization. And this is where the powers of CCA come in, because we were able to use machine learning adjacent tools, we implemented this in TensorFlow so that we would have auto differentiation and gradient descent enabled optimization techniques to actually make this tractable and able to run in a matter of minutes on a laptop. So this Wobbly result was a really cool sort of case study in the ways that you can use the vast amounts of data that you get from these surveys to kind of compensate for some of our theoretical shortcomings in not having, say, perfect telluric atmospheric models to still achieve extremely high precision. Yes, that good question. Yeah, so this is assuming that the stellar spectrum stays the same, and it does not. I have a whole section to talk about that I'm going to get to, but I will say it's completely standard. Every method of measuring radial velocities currently fundamentally assumes that the stellar spectrum is constant, which it's not, but I'll also mention that we're still developing this a little bit. So this was initially put in TensorFlow, but Matt Vaughn, a grad student at NYU, is now porting it over to JAX and modernizing it and making various improvements. And he's also applying it to non-EPRV use cases like Apogee. So stay tuned. But anyway, the original Wobbly works extremely well. So this is an example just showing two side-by-side Wobbly models, one for the Sun-like star, 51 Peg, and the other one for the late M-dwarf Barnard star. And you can see that even though the data and the stellar model are completely different for these super different stars, you get the same telluric lines out, which is a really nice sanity check that we are truly finding the right telluric lines. We also have radial velocities that work extremely well for these. We're able to recover the planet around 51 Peg and the secular RV change of Barnard's star as it actually physically moves relative to us. Finally, I'll just mention quickly that there's other projects related to this that I could get into. For one thing, the optimally co-added stellar spectra that you get from Wobbly enable really, really awesome stellar characterization work, including super high precision galactic chemical evolution measurements. And the lessons that we learned about tellurics from this project can be applied to other use cases, like the work that I did with Predoc, Arjun, Bedell on how tellurics affect our inference of exoplanet atmospheres. But I will stick with the Terra hunting experiment and RV exoplanet theme for now. And I will actually also skip past this because I'm taking a little longer than I meant to. Sorry, Lily, but Lily's work is coming back. This isn't her only chance to shine. Suffice it to say that we can also apply really cool data-driven sort of algorithms that take advantage of all of the amounts of data that we have to improve instrument calibration and wavelength solutions as well. And Lily has done some really awesome work on that, improving the express spectrograph's precision by a lot and changing their pipeline. Since I think it'll interest people in this audience, I wanted to spend a little bit of time talking about the stars. Specifically, as Amiel brought up, we have methods for measuring precise radial velocities from a stellar spectrum, assuming that it's constant. But is that true? Of course it's not. We know that stars change over a lot of different timescales. Sun-like stars are oscillating. They have convective cells that are overturning in the photosphere constantly. They have transient surface features like spots and plage. They rotate, so those surface features are moving even more because they're rotating across the surface of the star. And they have long-term activity cycles like the sun's 11-year magnetic activity cycle. And all of these things cause signals in the radial velocities that we measure. And this is widely regarded as a major roadblock in finding Earth-like exoplanets. So to illustrate exactly why something like this is a problem, this is a nice demonstration using code made by Rodrigo Luker, Starry, where we take a star, we put one spot on it, we rotate that spot across the surface of the star for a rotation period, and we look at what one stellar line in the spectrum does in response. So you'll notice that where the sort of rest state of the spectrum is a Gaussian-ish line, as soon as the spot starts to appear, while it's on the blue shifted half of the star, the half of the star that's rotating towards you, the dark spot sort of takes a chunk out of the blue shifted half of the line. And in the residuals to the line away from that Gaussian, you start to see that there's asymmetry happening in the line. Once the line crosses over the mid plane of the star and moves on to the half of the star that's rotating away from you or redshifted, the asymmetry reverses. So you get what looks like a periodic signal of blue shift and redshift just from a star rotating across the surface. If you treat the spectrum as a constant Gaussian, you're going to learn biased radial velocities from this. So we have to find a better way. In true Rodrigo fashion, we went all the way to the completely principled, fully Bayesian approach to inferring the stellar surface and the spectrum that emerges from each part of the surface, assuming that the spot and the quiet star surface have different emergent spectra, and being able to infer simultaneously the map of the stellar surface, what those spectra look like, and how they're changing through time. This was a really, really awesome piece of work that was enabled by the fact that Rodrigo's Starry code does fast analytic approximations based on spherical harmonics that make it actually computationally tractable to do these forward models of what the stellar spectrum looks like from the surface map quickly enough to do a Bayesian analysis. You can check out the paper. He applied this to a brown dwarf and inferred a surface map for it. It's very cool.
Did the surface map say spot?
It did not. This is a demonstration of a spotted star. We have yet to find a real brown dwarf that says spot. I'm sure it's out there, like statistically. Somewhere in the universe. Yeah. So this is an awesome demonstration of kind of where we want to get to. It makes very stringent demands on the data quality and quantity. And so we wanted to have something that's a little more able to go out of the box on the current in-hand radial velocity data sets. So this is something that Lily Zhao has been working on with me and Hogg. We are developing a data-driven model of how the stellar spectrum varies by essentially we're inspired by the understanding that the star has a coherent map of the stellar surface. And we have a time series that's a bunch of snapshots of that surface. If we use our time series with something like PCA to reduce dimensionality, we can essentially break it down into the representative components that come from different parts of the signature of the spot. And we can then use that basis that we've constructed to figure out where in this space of possible stellar variations do we currently sit, and how do we then correct the current radial velocity measurement based on that. This is ongoing work, so stay tuned for more and probably a much better explanation from Lily at some point. But we have some cool results already, and I'm very excited about this work.
ask, this uses the radial velocities or the radial velocities and the spectrum?
It uses both the radial velocities and the spectrum. And in fact, it mostly uses the full spectrum. Yeah. Okay, I'll quickly mention also, so we're chipping away on this problem of stellar variability on a lot of different fronts. And the previous things I talked about were taking the full spectrum and trying to properly model how it's changing with the stellar variability. But another approach that you can take and that many people do take in the literature is to say, okay, my radial velocities include stellar variability. How do I model that in the time series of the radial velocities and separate it from the planet signal? So this is something that we worked on with Quang Tran, a pre-doc. He is currently a UT Austin grad student and about to graduate and go to Yale as a 51 Peg Fellow. So we'll have him around soon, which I'm very excited about. Quang had a data set of very active young stars, and he also had simultaneous photometry for some of them. So having that photometry is super useful because it gives you independent information about the activity and the spot coverage at a given time. But it's a little complicated to compute the model for what the star is doing in both photometry and radial velocities simultaneously. So with Quang, we developed an approach that's based on Gaussian processes and the exact form of how those Gaussian processes are summed and differenced to go into the photometry and radial velocities is informed by the physical understanding of the spot. So we developed this method. Quang did a lot of work doing really principled tests on this and found that the method performs very well, outperforms what's currently in use in the field, and he's currently using this on his real data. This is a simulated data test to hopefully find lots of new exoplanets around active young stars. I will say, looking forward into the future, I think the stellar astrophysics and stellar variability will probably be, honestly, the first science results of the Terra hunting experiment before we get down to any exoplanets. So I'm interested in looking forward to the future and trying to understand scientifically more about what we can learn about stars and their behavior with these data sets. I think this meshes really well with the stars and plasma astrophysics interests in moving towards 3D MHD models of stars, and also with CCA investments in stellar astrophysics and things like MESA and SDSS-5. And this also involves a broad global community. We had a really great workshop around this time last year called the Sun as a Star workshop that we held across the street, where we invited astrophysicists and heliophysicists to come together and talk about what we can learn about solar variability from the data sets that we're gathering here. And that was super useful and spawned a lot of cool projects. So I think that the future is bright in terms of learning about stars and hopefully also helping us break the barrier of stellar variability and get more exoplanets too. I've been talking a lot about what we can do with data that we have in hand, but I also want to talk a little bit about the experimental design of the survey and what data we get and when we get it and how we're thinking about that. Because as I mentioned earlier, this is a time-sensitive thing to get correct right now for the Terra hunting experiment. We're thinking and talking a lot about things like target selection and survey design and observation strategy. So something that I worked on with Arvind Gupta was this question of how do we set up our observing strategy? This is just an example to illustrate that these surveys get complicated over the course of a couple of years. You're revisiting the same sets of stars many, many, many times. And you want to space out those time investments in a clever way so that you're getting information about changes on the time scales that are most relevant to the things you want to learn about. So we're facing questions of like, how many times per night do I visit a certain star? How many times per week or month do I revisit it? How many times per year do I allocate to this star at the cost of observing other stars in the program? How do I balance all of that so that I get the best return on Earth-like planets or whatever my science goal is here? And Arvind and I thought that the answer to this is using a Fisher information approach. This is, I think, probably old news for the cosmologists, but it wasn't something that had been done a lot in exoplanet science. Basically, the sort of information theory approach allows you to take the proposed observation times. You make assumptions about the model of the planet that you're looking for and the correlated noise that's in the way of finding it. And you can compute for the given observation times what measurement precision you're going to get out at the end. In this case, the measurement precision is sigma k, that's the uncertainty on the radial velocity semi-amplitude of the planet, and that corresponds to the mass of the planet. That's the main thing we want to measure. And having a highly precise measurement of the mass of the planet also means that you have measured that the mass is non-zero, which means you detected the planet at high significance. So Arvind and I built a framework to use all of the different stellar variability components that we know to worry about and put those in as correlated noise structure in the form of Gaussian processes to calculate what kind of precision we can expect for different proposed survey strategies. And we broke it down along a lot of different axes. One of the questions we were asking was, within a night, how many times should you observe the star and how spread out throughout the night should those observations be? So ranging from the baseline of just one observation in the gray line to the most extreme of 6 individual observations spread out across the course of the night. What gives you the lowest sigma k, the lowest uncertainty on the measurement that you're interested in? And you'll notice here that there are 2 different effects: oscillations, so the like P mode, approximately 5-minute oscillations of the sun or sun-like star, and granulation, which is the overturn of the convective cells. This tends to show up on several hour timescales. And those 2 things directly compete with each other for which strategy is best. For oscillations, you prefer to stay on the star for a while to see the coherent oscillations, because you can really nail those down in just one visit. For granulation, which is spread out more across the course of several hours, you want to keep revisiting the star throughout the night so that you get multiple samples across the granulation cycle of the evening. The quantitative framework that we have here is really important to help see which of these 2 things wins for a given stellar type. What we found is that it's a tight competition, but in most cases, assuming that you're willing to spend 20+ minutes per night on a star, for a sun-like star, you want to do the single visit strategy. One interesting thing to note is that if you wanted to do a super fast visit to each star, you're actually best off doing something a little bit in the middle and trying to break things down a little bit more. And this may be relevant for things like the Keck Planet Finder that have extremely large aperture telescopes and can afford to just spend a couple minutes integrating on a star.
There's some cases where you can spend more time on a given strategy and your answer gets worse. Like they don't all the curves don't go purely downwards.
Yeah, no, that's right. That's right. So I guess for the case of oscillations here, you do sometimes get worse. And that's because you're observing. So as you move on the total time cost, since the number of observations is fixed, you're basically changing the integration time of the exposure. And there are certain integration times that are pessimal for a short period oscillation. If you observe exactly over, say, half an oscillation, then you're,
This is for a star with a particular period. I see.
yeah, that's right. Yeah, so it's important to note that all of this changes with your star, and the covariance matrix that we're using to calculate the Fisher information is tuned to a particular star. So we were doing this for surveys that look at sun-like stars, and this tends to be the answer for sun-like stars, but for other stars, it'll be different.
Are your detectors up the ramp?
They are not up the ramp. Some near-infrared spectra gas do that.
Keying up lands.
Yeah.
And the likelihood that you use for the Fisher is Gaussian, or because usually these kind of things will work well if it's a Gaussian, but it has like long tails and these kind of things. Then you trust your Fisher to some extent.
Yeah, we're assuming it's Gaussian. Yeah.
But it's a good approximation.
I think it's a good approximation. We could talk more about it later, but yeah. So the oscillations and the granulation are interesting to think about for within a night observation scheduling. Another question we wanted to ask was across multiple nights, across seasons or even years, how should we allocate the observations? So these are different sorts of strategies that we could use across the course of a whole observing season. Do we try to spread out the observations evenly across the season? Do we observe them in short bursts? Do we try to make sure that they're all boom, 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 one night after another, even if that means doing it only for a shorter part of the season because you can't afford to do the whole season? And we tested this for a couple of different cases of types and amplitudes of stellar noise. Both of these cases are actually both consistent with what we think that the sun does, depending on different surveys and different analyses. But you can think of it as like the optimistic case or the pessimistic case. And we actually find that the recommendation for how you should allocate the nights differs depending on the detailed behavior of the star. So one of our conclusions here was that it's really top priority to sit on some of the stars that we're interested in and that are representative of the sort of stellar variability that we're seeing, and figure out which of these scenarios is more likely, because that will directly impact our performance. Shirley.
Can I ask, like, because you only look at like 20 stars or so, right? How did you select those 20? Like, what prior information that you make you sit at the basically 20 candidates?
Yeah, that's a really good question. So for the Terra hunting experiment, this is still being debated which criteria exactly we want to use. The stars that I used with Arvind have already been locked in for his survey, which is the NUID Earth Twin survey. And basically, like, the number one criterion is bright. Well, I guess the top three criterion are like bright, nearby, and in the right declination range to have a very long observing season, so you can get a lot of observations per night. But there are things that are more closely tied to the stellar astrophysics that you can also consider. So you can do things like check in the chromospheric emission lines to see how magnetically active the star seems to be. If there's chromospheric emission, then you start to get suspicious that maybe it's not a well-behaved star for these purposes. You can do things like scaling different things with stellar mass to figure out what you expect the amplitude of different stellar signals to be, and also the amplitude of a planet reflex motion. Yeah, there's many things you can potentially do.
Just so I'm understanding, like, these are factor 2 differences.
Yeah.
So it's like the difference between like a 10-year survey and a 40-year survey?
No, these are both 10-year surveys. They're
No,
assuming.
I mean, the effective.
Oh,
Like,
yes.
to do as well with the green, you'd have to go for 40 years. Is that the meaning of this?
Yeah.
Okay, that's a big difference.
Yeah.
Good thing they did this.
Yes.
Actually, what's shocking is how few projects have done such studies, actually, when you think about it.
Yeah. Yeah, I'm not aware of anyone really doing this before. I think there was common knowledge in the field that that green strategy in particular is really bad. And the reason we put it in there is that that's what historically we have always gotten, because when you're observing bright stars, you get full moon time. So you end up executing your surveys along the green line. And it was noticed that that was not good in terms of like.
But you have to use the quasars in the darker part.
I know. You're part of the problem. No, I think, well, so these days we have more of these spectrographs, the EPRV spectrographs that are going onto dedicated telescopes, because we really don't need large telescopes for these purposes when we're looking at bright stars. So we have a lot more flexibility now, and we don't have to compete with the quasars so much these days. But yeah, in the beginning, maybe there was no point in doing this calculation because you were going to have to take the green line and be happy with it. I don't know. Okay, I finally also want to mention, related to this, that many of you may have met Chris Lamb, also past pre-doc care. Chris took kind of a part of this project and spun off into focusing on the follow-up of known transiting planets around very active stars. These are being found in large numbers by TESS and need follow-up, and it gets really complicated to figure out how do you allocate your observing nights when the planet signal and the stellar signal are similar in frequency to each other. So Chris did some really cool detailed work, like looking into interpreting exactly why do different observing strategies work and not work. And he is making an open source tool for observers to use in helping to plan their strategies, and very excited about this. I think also this sort of work on like the information content of observations and how that translates into science will potentially be useful and applicable in things like prioritizing LSST follow-up. So I'm interested in kind of thinking about that stuff going forward as well.
You have 10-ish minutes.
Oh, that's longer than I thought.
Well, it depends on, she's 4 minutes.
Okay, okay. I'm gonna take 5 minutes
Good.
at most. Okay, but to come back full circle on Arvin's project, which was looking for a terra hunting experiment like surveys, the question that we can now ask is, will the terra hunting experiment find an Earth? And the answer, of course, depends on whether our optimistic or pessimistic noise model was better. But I think the answer is probably yes. Even in the pessimistic case where we're looking at like 1 sigma detection significance on an Earth, this is all assuming that all of the stellar noise mitigation stuff that I was talking about previously, in terms of finding better ways of modeling the spectral variability, better models of treating it using ancillary data like photometry, that all of that, none of that is factored into this. So I'm cautiously optimistic that we will be able to find an Earth-like planet, even in the worst case scenario. But it's enough of a question that we really do need to have a carefully designed survey, and we need those improvements in the data analysis. So I will wrap up by zooming out a tiny bit. I've been talking all about Earth 2.0, and I hope that I've shown you that finding Earths is a hard endeavor, and that in current research, we're really working hard on pushing this forward on a lot of different fronts, ranging from the top level survey design to the data analysis questions involved here. But I started the talk by saying that I'm interested in putting the solar system in context as a whole with other star planet systems, and that does go beyond Earth's. So I'm really looking forward in the future to learning about multi-planet systems across a wide range of scales by combining lots of different missions and types of observations. In particular, I'm really excited about astrometry and Gaia DR4, because that's going to completely revolutionize our understanding of Jupiter analogs, which are very important. I think it's really cool to think that TESS and Plato are finding all of the transiting planets around nearby stars. So that means that by putting together transits, radial velocities, astrometry, direct imaging, that all target nearby stars, we'll be getting as complete a picture as possible about stars in all different orbits around the closest, or planets in all different orbits around the closest stars to us. And I'm really excited about kind of the challenge of fitting together the puzzle pieces of these different methods. I think CCA is a great place to approach this problem. And of course, the stars will have a lot of things to teach us along the way. And with a different hat on, I'm interested in the stellar abundances, stellar properties, things that we can learn about specifically how the sun compares to other sun-like stars and what that might mean for our solar system. So I will wrap up with takeaways. Finding other Earths is hard and requires innovations. CCA is a good place to do this. And in particular, we've really been able to build lots of collaborations. I mentioned a lot of people and collaborators from a lot of different universities, also from a lot of different instrument teams that I've been working with, which is only possible because CCA is such a great place to kind of be a neutral, positive territory for everyone to work together. We're doing a lot of this out in the open with open source implementations of codes. So I think this really helps to make sure that the work that we do benefits everybody, not just the Terra hunting experiment and other surveys like that. While we're doing these improvements for searching for Earths, we're also learning a lot along the way about stars and how to do astronomical surveys and all kinds of cool things that apply to other fields as well. So thank you very much for your time.
We have time for questions, and I'm going to let Megan recognize the question askers.
The optimistic and pessimistic, are those purely empirical, or do they have some sort of physical understanding of something different assumed about the sun that gives rise to those?
They're both empirical. The form of the two, so they're based on two different sort of correlated noise models that are both empirically guided, but I would say one of them, actually the pessimistic one, is a little bit more informed by the physical picture of like rotating spots, is more baked into the form of the model. But they're both very empirical, and therefore I think they both will get better as we get more data, which we are. Yeah.
Hi, great talk. I'm Tim Manning, visiting from Sydney for a few days. I work in astroseismology, so you can guess what I'm going to ask you about.
Great.
So if you go back to how you fit the spectral, how everyone fits the spectrum, they assume that it slides backwards and forwards. But when a star oscillates, the core of the line moves more than the wings because the cores form higher up in the atmosphere. And that's just how oscillations work. My question is that taken into account, or could it be, and would it help?
That's a really good question. So for both oscillations and also we think granulation, the depth of formation of the line matters a lot. And there has been really good progress made in terms of trying to parameterize the spectrum in terms of the depth of formation of each pixel of the spectrum, basically. And basically decorrelating against that when getting the radial velocities. I would love to talk more about whether there are like better ways to sort of forward model that more from the physics of it. But I think that the preliminary results show that that sort of approach does do better, and it makes sense that it should. Yeah.
Very brief question. You said that you need to get to 10 centimeters per second. What is the best number that now exists for less variable velocity?
It depends. It's hard to define what thing you should be looking at here. So one metric is the lowest amplitude radial velocity exoplanet that has been securely found. And that's about 0.5 meter per second. Another, like the most optimistic possible thing is to look at the instrument stability itself and compare like calibration data across time. And most of the EPRV spectrographs find instrumental stability at the couple of centimeters per second level. But it's,
That's not what you're really worried about. You're worried about the stars. So
yeah, you're mostly worried about the star itself.
it's 50 centimeters per second. Been there for a while.
No,
Oh, that's new.
that's pretty new. Yeah.
But it's been a meter for a while. Right?
It's been a meter for a while, yeah. And there have been, I mean, there's a long and controversial history of claims of sub-meter per second planets that then get debunked later. So it depends what source you're looking at. There's one that I believe that's 0.5 meter per second. That's quite recent. Julianne.
Yeah, I'm just wondering, like, you can set up this optimal survey thing, but like, 5 years in, you might be getting pretty sure that, star X is not are there ways to structure this so that it's kind of like surveying more stars initially and then going down, but still being able to keep doing principal, because you're trying to also do principal population statistics at the end, but you also don't want, you're doing all these things to optimize how to use the time, and it's all very confusing.
Yeah, yeah, we have talked about, and I think we probably will end up doing sort of a tiered survey design like that, where initial phases of the survey are partially dedicated to kind of gathering all of the information that we need to make the principled decisions about which stars to look at further in the next tiers. And I think that's the right approach.
So uniform within.
Yeah. I think the key is to be able to have reproducible cuts, to write down exactly what you're cutting on. And the past state of the art is like the cuts are made on vibes based on like what the observer is feeling from that star that night. We can definitely do better than that.
Definitely.
But I guess
Yeah.
maybe that also kind of get Mike's question, like I'm sure that there's probably, it's going to be a while till you actually have like the instrument on sky and take but given that some of these things and strategies are based upon having a better understanding of the star, like, are there teams that are doing a lot of pre-imaging of these things or sharing information among the different instruments that are already looking?
Mm-hmm. Yeah, I would say the most work along these lines, like learning more about the stars and sharing information, has been done for the sun, actually, because that's the target that all observatories can agree on, because it's the only one that they can do during the daytime. So they install a little solar telescope and send it through the same instrument that they use at night. And there's like 5 or 6 different instruments doing this now. And there has been a lot of progress made on just with like the vast quantity and quality of data that you can get on the sun, on trying to learn more about its detailed behavior and testing out different mitigation methods on the sun. How that generalizes to other stars is an open question. And there is work going into trying to define sort of community standard stars for which data will be shared. But there's various like political and logistical hurdles that has made that not really happen yet. Shirley?
I'm just curious, when you say search for Earth, does it have to be habitable or does it just have to be the right size?
So it depends which questions you want to answer. To me, I'm most interested in within the habitable zone in terms of, approximately Earth-like orbits. Honestly, although I'm interested in aliens, I'm mostly interested in like the formation questions around the Earth. And so for that, it doesn't strictly need to be within the habitable zone, but something like a super hot Earth that has likely or possibly migrated to where it is not ideal. And that's the only thing we can find right now.
The reason I asked this is because the variability of the sun might affect the habitability of the Earth that we find. And that's why I was curious about that survey optimization question, given you have information about.
Yeah. So you're saying that maybe we would want to have criteria related to the variability from like an enabling habitability perspective. Yeah, it's an interesting thought. I don't think that we know anything with enough confidence to warrant making a cut like that. And I would be worried about what sorts of biases we're introducing. But it's certainly worth thinking about. Yeah. Sabina.
Yeah, I have a question. So I guess I'm curious how problematic could spots be for sort of condition finding first analog, because in the when you showed the Rodrigo's just like deviation of the delta in the spectra, the spot that started produces and the spot that was like in your images are pretty big.
Yeah.
But if you look at the sun analog, then those spots are probably going to be smaller. So would they be problematic, or could you just for your first for searching first analog, so could you just like neglect?
Yeah. It's definitely true that the amplitude of the spot signals will be lower because they're smaller. On the other hand, the sun and stars like it do tend to have complexes of multiple spots, which further confuses the signals. And there's also effects like the convective blue shift inhibition that seem to actually be the dominant thing, the like magnetic disruptions due to the spots. So I think for all of those reasons, and also empirically speaking, we see that that this magnetic activity tends to be at the level of 0.5 meter per second or more in the solar RV time series. We do have one thing working in our favor, which is that the time scales of those spots are generally going to be like rotation periods. And so they're not going to be super easily confused with a planet signal, but they still contain correlated noise that can bias the measurements in complicated ways if we don't account for it.
I hate to interrupt the discussion, but I have to know that there is wine out there. And so I think we should thank Megan for the talk.